Good morning, everyone. Thanks to everyone who's joined. Let's make a start. I'm sure there'll be others joining, but that's fine. It's just a brief kind of introduction and hello for me. So my name is Matt Palmer. I'm a Science Fellow at the Met Office. I'm one of the joint directors of the UK National Climate Science Partnership, and my role here today is really to welcome you and thank you for coming to this webinar. The webinar has been put together by the Sea Level Working Group. So Rosie and Ines from the working group will take us through the main science presentation today. But before we do that, I'm going to pass to my colleague Wendy, who will take us through some of the housekeeping today and also give you a brief overview of the UK National Climate Science Partnership before we move into the main science presentation. So over to you, Wendy. Thanks.
Thank you very much, Matt. And yes, next slide, please. So yeah, before we start the presentation today, I like to do some housekeeping first. So if you're asking questions, please use the Q&A function by clicking on the tool icon, which should be on the bottom right of your screen. So please do not put questions in the chat. And also please keep yourself muted to avoid noise disruption during the presentation. And the last thing is that please note that this webinar is being recorded and we will circulate the slide deck and the recording afterwards. Next slide, please. So hello and welcome everyone again to join the webinar today. I am Wendy Tai and I am the Program Manager of the UK National Climate Science Partnership, which is also known as UKNCSP. Next slide, please. So what is UKNCSP? We are a relatively new national initiative, and this is a joint partnership that includes the Met Office and the 6 NERC-funded research institutes, as you can see listed below. Next slide, please. So what exactly is the partnership doing? We actively coordinate research across different institutes, and we constantly looking for key gaps and opportunities in the generation of climate science. We also try to influence funding landscape to promote those crucial long-term observations and modeling capabilities that underpin our work. And more importantly, we want to make sure that the research outcomes are useful and have real-world impact on the policy and the society. So we actually do quite a lot of things on stakeholder engagement. Next slide, please. We proactively engage with quite a wide range of stakeholders from the public to the private sectors. We are creating a mutual way of communication to understand what the stakeholders need from the research community. And we also showcase what the scientific evidence is, just like the webinar today. So the UK NCSP not only acts as a hub for climate science, we're also keen to have conversations with decision makers and users of climate science so we can help develop climate solutions together. Next slide, please. To achieve our goal, we focus a lot on knowledge integration. The aim is to maximize the impact of climate science research for all our stakeholders. With that in mind, we actually facilitate and support the provision of climate evidence and policy advice. And we also produce various outputs like briefings and explainers that are designed to effectively deliver the knowledge and the findings. Next slide, please. And to push forward all the efforts and activities, we actually have several working groups as our main force. The working groups are based on themes, and currently there are four of them focusing on climate interventions, climate modeling, climate observations, and sea level rise, which is the one that hosting the webinar today. And each working group has different scopes, but they are all working on making scientific findings accessible and useful to those who need it. And of course, we're not restricted to only have 4 working groups. It's highly likely another new one will be established soon, and we look forward to providing more updates once we have firmer details. Next slide, please. So there's not enough time here to talk about the details of what each working group is doing, but we now have an official UK NCSP website. So if you want to know more about us, please do visit our website by scanning this QR code, and you will find more information. Next slide, please. The things I can highlight here is how you can directly interact with us. We have quite a quite a few activities that are open to all the audience. Just like today, we have 3 webinars across different topics. And by joining the webinar, you can have the direct conversations with the working group members. And we also put the previous webinar recordings on our YouTube channel, so you can always replay them. Next slide, please. Other than webinars, we sometimes also have invited-only events, mostly aiming for facilitating large-scale cross-institute research ideas. It is also quite often that the working group will launch surveys. So for example, the Climate Observations Working Group are now investigating the needs and gaps in the current observation data. So please help us fill in the form because your inputs are very valuable to us. Next slide, please. And also welcome to contact us if you have questions, things you'd like to discuss further. We have Mike and Matt as the joint directors and Rose as the knowledge integration lead. And I think we're both here in the webinar today as well, so feel free to reach out us anytime. Next slide, please. And finally, please follow us on LinkedIn as well as our main social media platform, so you will get all the updates about our activities or any news about any funding opportunities. And I will stop here. Thank you very much. I'll hand over to Ines.
Hi, everyone. Thank you, Wendy, for the introduction about what we're trying to do through the UK NCSP. But we're going to now turn to our main topic today, which is sea level uncertainties from the ice sheets. So in this webinar, we're really going to focus on the ice sheets. We're going to explain why they matter so much in any discussion related to sea level rise, and we'll provide an overview of the recent past and future changes of the ice sheets. So questions that we're going to try to answer today are the following. First one is, what are the current and future contributions of the ice sheets to sea level rise? What evidence do we have that the ice sheets are changing? Why are the ice sheets are the largest source of uncertainties in future sea level rise projections? And we'll also end this webinar by talking a little bit about what it means for the UK. So my name is Ines Otosaka. I work in the Centre for Polar Observation and Modelling, CPOM, at Northumbria, and my main expertise is in using satellite observations to detect changes in the ice sheets and estimate their contributions to sea level rise. So I'll cover the current state of the ice sheets, and then my colleague, Rosie Williams from Bath, who is an expert in ice sheet modelling, will then cover the future state of the ice sheets. So just to start off, so here is an animation showing snow cover and sea ice in the northern and southern hemisphere, just to provide you with an overview of what we're looking at. So here, just the polar regions, and what we're interested in is the Greenland ice sheet located here, and then the Antarctic ice sheet. So you can see that the polar regions in the two hemispheres are in very different configurations. So in the northern hemisphere, you have the Arctic Ocean that is partially covered by sea ice most of the year. And the Arctic Ocean is surrounded by land, which include the Greenland ice sheet. While in the southern hemisphere, you have the Antarctic ice sheet, so a continent that is surrounded by ocean. Another important thing to note is the size of the ice sheets. So Greenland is around 9 times larger than the UK, but Antarctica is much bigger. It's around 50 times larger than the UK. So we know that the polar regions are changing, and we know that the ice sheets are contributing to sea level rise. But first, I'd like just to take a step back and just show you a curve that represents the global mean sea level over time. So we have good measurements of sea level changes since around 1993, thanks to satellite altimeters surveying the world's oceans. And you can see from this curve that mean sea level has risen by 11.5 centimeters since the start of our observations. So sea level is not rising uniformly across the world. If you look at local scales, there are some very important local processes, such as vertical land motion, that play a large part. But on average, if you just look at the world ocean and just take the average, we can say with confidence that sea level has risen by 11.5 centimeters since 1993. And there are several factors that are responsible for the sea level rise. So the first one is the thermal expansion of the oceans. So as the ocean warms, they take up more space. of the one that we're interested in today, and that's really getting even more important and will be a major contributor in the future, is land ice melting. So this includes melting from land ice, so from the two ice sheets and from the glaciers. And also a smaller component is the changes in land water storage, so for instance, because of irrigation. So now if we superimpose the ice sheet's contributions to global mean sea level on top of the previous curve, you can see that the ice sheets contributed around 2.8 centimeters since 1993. And if you look at the proportion of that compared to the whole sea level rise that we've observed, that's around 1/4 of all sea level rise. So just using this kind of recent sea satellite records, it's obvious already that the ice sheets are already a major driver of sea level rise. So when the ice sheets lose mass, it's a source of fresh water to the oceans, and then it contributes to rising the global mean sea level. And so I just would like to spend a little bit of time now to just go through the main drivers of ice sheet mass changes. So the first one stems from their interaction with the atmosphere, and it's what we call surface mass balance processes. So it includes all of the processes that are occurring at the surface of the ice sheets. So for instance, it includes precipitation, snow or rain, which is the main input of mass to the ice sheets. So the main mechanism for ice sheets to grow is through snowfall accumulation. And it also includes surface processes that leads to a mass loss, such as a surface melt and runoff. So for instance, in summer, you have lots of surface melt in Greenland, and then this melt water can just run off the ice sheet, and then that contributes to a mass loss. And the second driver of ice sheet mass changes, and here is the mass loss, refers to ice dynamical processes, and these include processes that determine the rate at which ice flow from the ice sheets to the oceans. So if you have an ice sheet, so the ice is being transported by ice streams from the interior of the ice sheets to its edges, and it then interacts with the oceans. And the solid ice that is being transported out of the ice sheets to the ocean is termed ice discharge, and that constitutes a source of mass loss. So to summarize, the ice sheets interact with their atmosphere and with the oceans, and when we measure the mass balance, it means that we measure the mass gains and mass losses, which are basically the results of surface mass balance and ice dynamical processes. So how do we do that in practice? So to help us collect some very important measurements about the ice sheet state and the health of the ice sheets, we can collect in situ observations to help us understand these different processes. So here is a map of the main research stations in Antarctica. So obviously, as I've mentioned, Antarctica is 50 times larger than the UK. So those are quite sparse, but they are very important location because they help us reach some very important location on the ice sheets, and to reach those different research stations where then scientists can go there and be deployed in the field to make their important measurements. We can use ships or airplanes. So here is, for instance, a picture of the Sir David Attenborough research vessel. And here is a picture of a twin otter, a small plane that can actually land on ice, bringing scientists into the field so that they can make, for instance, geophysical measurements. So in situ measurements that can be collected include measurements of ocean parameters, such as ocean temperature, ocean salinity, which are really, really important so that we can better understand ice-ocean interactions. We can also collect measurements using airborne sensors. So for instance, measurements of the ice sheet bed topography and surface elevation so that we can determine the ice thickness. Also GPS stations and automatic weather stations also installed in some places around the ice sheets. And we can also, of course, collect ice cores or measure also surface mass balance using stakes. And those are really key measurements. But of course, collecting field measurements in the polar regions is something that's very challenging. It's a very extreme and remote environment, so it's expensive and logistically challenging to deploy instruments and collect data there. So while we really need those measurements to learn more about the processes that can lead to ice sheet mass changes and to an increase in sea level rise, it's really important to also complement these measurements with satellite observations. so that with satellite observation, we can get a full coverage of the ice sheets. And that's great because since the 1990s, so the space agencies, so for instance, the European Space Agency, ESA, NASA, and also other national agencies have launched satellite missions into space dedicated really to the monitoring of the polar regions, because they know they're changing rapidly. So it's really important that we have some means of monitoring what's happening in the polar regions. And here are just some of those satellite missions. So for instance, in the center here, in Europe, we have Cryosat-2, which was launched in 2010 and is still collecting some very important measurements of sea ice thickness and ice sheet elevation changes 15 years after its launch. So it was well past its life expectancy. So over the ice sheets, these satellites really help us monitor some key indicators of the ice sheet's health. So the first variable that we can measure at ice sheet wide scale is ice velocity. So here are just some maps of Antarctica and of Greenland ice velocity. So basically it tells us how fast the ice is moving. So here in purple, you have the fast flowing sections of the ice sheets. So the ice sheets, as I've mentioned before, so the ice is being transported from the interior of the ice sheets to the edge of the ice sheets toward the ocean through those fast moving ice streams. And all of those areas in purple and pink are really fast-flowing regions of the ice sheets. So for instance, region that we're going to come back later because it's really important when talking about sea level rise is West Antarctica. And you might have heard of two important glaciers there that draw a large part of this area in Antarctica, and that's Pine Island Glacier over there, and then Thwaites Glacier's its neighboring glacier. And they are the largest contributors to sea level rise in Antarctica, and these glaciers typically flow at speed faster than 1 kilometer per year. And another key measurement that we can get from satellites are surface elevation changes. So basically from space, we can also map areas that are thinning, so that are melting, and areas that are thickening, where, for instance, snowfall is accumulating. And you can see that we have lots of red areas located mainly around West Antarctica. And any area colored in red is a rapidly thinning area, so a glacier that is losing more than 1 meter of ice per year. So in Antarctica, it's really concentrated around the margin of West Antarctica. And in Greenland, you can see that it's all across the ice sheet, especially on the west coast of Greenland. And then, of course, we can use those measurements to measure ice sheet mass changes. So we actually have several satellite techniques to do this. And what you can see is that the pattern of mass change match with the pattern of thinning that I just showed on the previous slide. So West Antarctica is currently losing a lot of mass in Antarctica, and Greenland is overall losing a lot of mass too. So we have now more than 30 years of satellite measurements of ice velocity, elevation changes, and mass changes over the ice sheets. And those long-time records are very helpful for tracking changes. But what satellite observations have also helped us to do is also realize that some of the changes that are happening in the polar regions and in the ice sheets can also occur on much shorter timescales and sometimes much shorter than what we previously thought. So I'd like to take an example of one of those rapid change that was observed during the satellite record. And the prime example of that is the collapse of the Larsen B ice shelf at the Antarctic Peninsula back in 2002. So ice shelves are the floating ice platforms that fringe around 1/3 of the Antarctic ice sheet. So they form when the ice that flows from the interior of the ice sheet meets the ocean and starts to float. So it's different from sea ice because sea ice is formed from frozen seawater, but ice shelves are formed from glacier ice. So ice shelves in Antarctica can be very large, and they can range in thickness from around 50 to 600 meters. So there are huge platforms of ice really that are floating on the ocean. And they play a very important role in stabilizing the ice sheets because they prevent the grounded ice that is upstream from flowing too rapidly to the ocean. So they act as a kind of barrier. So they're really important for the stability of the ice sheet, even if they don't directly contribute to sea level rise. And the Larsen B ice shelf disintegrated in only 35 days. So here's a succession of events. So you have a satellite image from an optical satellite image from at the end of January. So you can see the ice shelf over there, and there are some meltwater on top of the ice shelf. And then you can see a bit later, there are some bits of the ice shelf that have broken off, but then it dramatically goes quicker, and you can see that this whole area is just disintegrated. So that was a very large event, because basically the size of Cornwall disintegrated over the course of a month. And also following this disintegration, we then observed a speed up of the glaciers that are located upstream. So that's another thing that satellite observations have really revealed, is that even if the response time of the ice sheets is slower than compared to other components of the Earth system, they can still react quickly, and there's still much to learn about the triggers that can lead to such dramatic changes. So now, if we go back to the long time series of ice sheet mass balance that we can derive from satellite observations, it really tells us about the contribution of the ice sheets to sea level rise over time. So this graph here shows the cumulative mass change of the ice sheets over time from the 1970s to 2024. And here I'm showing Greenland in blue, Antarctica in purple, and also Antarctica divided into three main areas. So West Antarctica in green, East Antarctica in yellow, and then in red the peninsula where Larsen was located. And looking at this data, we can say that together Greenland and Antarctica lost more than 11 trillion tons of ice since 1979, which is a huge amount of ice, and that's equivalent to contribute to rising the global mean sea level by 3.2 centimeters. So this satellite record also shows that there has been an acceleration in the pace of mass loss. So at the beginning of the record, the ice sheets were not doing very much, and you can see after that that the trend has accelerated. If we look at the decadal rate of mass change, we can say that the ice sheets are now losing mass around 4 times faster than in the 1980s. And other important point to note here, even though the Greenland ice sheet is much smaller than Antarctica, it's currently losing mass faster. And also in Antarctica, I've talked a lot about those glaciers in West Antarctica, and you can see that in Antarctica, most of the ice loss originates from West Antarctica. So far, I hope I've managed to showcase how satellite observations have advanced our understanding of the changes happening in Greenland and Antarctica. Sometimes it's occurring even faster than we thought. So here I just would like, before I hand over to Rosie, to show you a quick animation. So here is a curve I just showed you. So that's the INBI curve is those observations. So the contributions of the ice sheets to sea level rise. And now if you add the projections from computer models about what would happen in the future, you can see that the observations are tracking as these red lines, which are representing the worst climate warming scenario. So it shows that observations are also critical so that we can really have an idea of what the future might hold for us. And it's really important for initializing, calibrating, and evaluating ice sheet models that then we can use to look into what the future might look like for the ice sheets. And on this, I will hand over to my colleague, Rosie, who's going to tell us more about ice sheet models.
That's brilliant. Thank you so much, Ines. So yes, in that video, we saw how we have measured ice loss from the ice sheets till the present day, and then going from the present day over the rest of the century, we use these models. So I'd like to unpack a little bit what's going on when we're making projections using an ice sheet model. So an ice sheet model is essentially a set of mathematical equations that describes, as Ines was describing earlier, the mass accumulation, so the snowfall on the surface of the ice sheet in this case, and then the dynamical flow of that ice out towards the margins, and then the ice loss through melting by the atmosphere and the ocean, and through carving at the edges where these big bergs break off and carve. And to use an ice sheet model to make projections, we combine our ice sheet models with observations. If you could just click, Ines, that would be great. We combine our models with observations such as those satellite observations we've just seen. These are incredibly useful for setting up our models. We also need to include key processes happening within the ice and at the margins of the ice. And this can include how the ocean melts the ice, how that carving process might happen, and how the ice is moving over its bed. And in our community, there are lots of different ice sheet models, and these are all slightly different in the way they approximate kind of the physics of the flow and the physics of what's going on in the ice, and in terms of how these processes are incorporated. And there are now really great developments in coupled modeling, so coupling ice sheet models with models of the climate or models of the ocean. But there's still a really powerful role for standalone ice sheet models to play. And if we're trying to make projections from those, then we can force our ice sheet model with output from the climate models, which come with their own uncertainties. But we can run our ice sheet model forward with output from a climate model under a specific future forcing scenario, so a specific scenario of emissions in the future, basically. And if you just click in this, then that's what we were looking at before in the video. So here we're looking at sea level contribution over time from the ice sheets, and all these different coloured lines you can see within those coloured bands. These are different combinations of ice sheet model, climate model output, and future forcing scenario in terms of emissions. And so you can see that there is quite a wide range of projections from this ensemble of ice sheet models over the next century. And so on the next slide, I'd like to just talk you through what are the uncertainties, where are they coming from, and how can kind of categorize them. And this schematic on the right is really nice for showing in different colors some of the different sources of uncertainties. So in black, we have the uncertainties that I've already alluded to, which are the uncertainties coming from the different ice sheet models, and then the different climates that are being used to force those ice sheet models, and from the fact that we don't know what the emissions are going to be like in the future. So we need to run our models under different scenarios, or different SSPs for people who are used to that term, but it's just different futures for how much greenhouse gases we're going to emit. We also have uncertainties in blue coming from the observations, and all those amazing satellite observations are really fantastic, and they mainly show us what's happening with on the surface of the ice, but getting observations from within the ice column, within that deep ice, and getting observations of what's happening at the base is much more challenging. They're very remote locations. The ice is kilometers thick in some places, so that's still an ongoing challenge. But we also have these sort of small scale processes that are going on around the ice sheet, and these can actually exert a really large control on that large scale behavior of the ice sheet over many hundreds of kilometers. And they include the melting of the ice by the ocean. So when the ocean melts the ice at a carving face or under these ice shelves that Ines described, then really small scale features in the shape of the ice and the shape of the bed, and in the ocean circulation where the ice and ocean meet in that boundary layer, that can affect melt rates, which can affect the speed at which the ice might retreat or even advance in the future. We've got the processes of cracks forming in the ice and fracture, and that can lead to this iceberg carving where large chunks of ice break off the ice front. And this is quite a challenge to include in large scale models. There's very variable length scales of this carving process, and it's also a sort of inherently discontinuous or discrete process going on. And so we model the ice in a sort of continuum way, as a continuous flow, like imagine a river flowing but more slowly. But these carving events are discrete events within that, and that poses a problem for modeling. We also have processes happening at the base, shown in green here, the basal sliding. So we need to capture the physics of how the ice actually slides over the bed and how that might vary in space and time. And all these processes, together with the combined with the flow of the ice, can lead to potential instability mechanisms in the future. And these instability mechanisms have the potential to really accelerate the loss of ice from the ice sheets, and it might tip the ice sheet into some sort of irreversible retreat in the future. So I'll talk you through those. Those are shown in yellow here. And the first one of these I'm going to talk about is the marine ice sheet instability. So this instability has been talked about in our community for a long time, since around the 70s. And this can occur when your ice sheet is resting on a downward sloping bed. So in West Antarctica, where Ines was saying a lot of the change is happening, the ice sheet is sitting on a bed that deepens as you go away from the coast and towards the interior. And what can happen here is the ice shelves, those floating tongues, they are melted by the ocean, and that causes the ice shelf to thin. And that, because that's buttressing or sort of holding back the inland ice, then the inland ice flows up, speeds up. And that area where the ice first goes afloat, the grounding line, then retreats. And because it's on a deepening bed, as it retreats, there's a larger area in contact with the ocean, and more ice is crossing that grounding line zone. And that leads to further retreat and further thinning. And this positive feedback is thought to be able to lead to unstable retreats. And it's possible that this could be an unstable retreat, such as when if you cool down the atmosphere and the ocean again, the ice may continue to retreat even in that scenario. And then the other potential instability mechanism is the marine ice cliff instability, and this has come into focus much more recently in our community, in maybe the last 10 or so years. And the idea here is that if you have increased surface temperatures over the ice shelves, then you get some surface melt, and that meltwater can flow into cracks or fractures or crevasses really in the ice that can then lead to hydrofracture, and it can lead to calving events and even really large-scale calving events or whole ice shelf collapse, as Ines described for Larsen B. And when that happens, when these large calving events happen, you're left with an ice front or an ice cliff, we might call it, which can be really tall. And it's hypothesized that there's a certain critical height for these cliffs above which they're just structurally unstable. They start to crumble away. And if that happens and the cliff crumbles away, then you leave an even taller cliff behind that. So then that will also crumble away, and you might get this instability and collapse mechanism. But it's important to say this mechanism is still really under discussion. We're still trying to work out as a community exactly how this might happen and might unfold in the future. And we're not seeing it at the moment for present day Antarctica. And on that note, I just wanted to cycle back to, on the next slide, to talking about calving again, because calving is actually really one of the grand challenges in ice sheet models. It's a really challenging process to model and incorporate, partly because the field sites where we want to observe and measure calving are really inaccessible, and they're really dangerous. It'd be hard to take your boat close to a calving front of a glacier. It wouldn't be a safe thing to do. We're really helped here by emerging technologies such as autonomous vehicles and drones that are allowing us to measure these in different ways now. As I mentioned before, they're also really highly variable in time and space, and that's a challenge when trying to incorporate into a model. But there's also the fact that this hydrofracture, that process that's a precursor to the marine ice cliff instability, or MICI, is highly parameterized in models. We don't yet have a full physical model of how that meltwater appears and then propagates around moves around the ice shelf surface and leads to hydrofracture and this potential mechanism. And that means that we don't have there's no general calving law yet that we can use in our models. But if we go to the next slide, then we can ask the question of what do models say about the future sea levels? And to make these projections, such as the ones shown here from the IPCC report, we use ensembles of models to project the ice sheet contribution to the sea level change. And this curve from the IPCC shows it's actually the global mean sea level change. So that's from all the sources, not just the ice sheets. And it shows it over time to 2100. And these different colored lines are different future emission scenarios. And the arrow shows that increasing emissions is going this way in the colors. And basically, as you increase your emissions, your sea level projections rise, which probably isn't terribly surprising. And there's some uncertainty associated with these shown by the colors. But on the next slide, we see that this IPCC report was really interesting because it also included these so-called high impact, low likelihood or hill scenarios. So these are scenarios that we're not confident will happen. They've got a low likelihood, but if they did, they could have really dramatic effects. And so it's important to include these when we're thinking about uncertainty in sea level rise. And these are shown by this dashed line on this figure here. And here you can see that if we think of in these sort of high-end storylines, we can't rule out 1.8 meters of sea level rise by 2100, but more alarmingly, by 2300, 15 meters or more of sea level rise cannot be ruled out. So we're not saying that's likely or that's in any way the most likely thing to happen, but we're saying we can't rule it out. And the way that this dashed line is obtained is through including that marine ice cliff, the MICI instability in the ice sheet models. So that instability mechanism could be really important in the future. And so it's really the poorly understood processes happening in the ice sheet that could lead to these large instabilities in the future that are causing all this uncertainty. If we go to the next slide, then this is also really nicely shown if we split this global mean sea level projection into its component parts. So this is, again, looking at that high impact storyline scenario from the IPCC report and splitting the sea level contribution into thermal expansion in red, Greenland in green, Antarctica in blue, and then glaciers and land waters too. And you can see that over time, the contribution to sea level from all these sources increases, but the contribution from the ice sheets, and especially from Antarctica, increases much more dramatically than the other sources, so that by 2150, the Antarctic ice sheet contribution really dominates the projections of sea level. And under this really uncertain scenario, that means that Antarctica is contributing a lot to that those levels of uncertainty. And then the next slide. So there are some end users in particular who will always be really risk averse and really will be very interested in these low likelihood, really high impact scenarios. So if we think of the millions of people living in the low-lying coastal regions in the UK, or where we have core infrastructure such as power stations near the coast, they're going to be very risk averse, and they're going to want to know or ask the question of when will we know if we're entering one of these high-end scenarios? Or another way to put that is, can we build early warning systems for the ice sheet? And some of you will have heard of ARIA, which is a new big UK funding agency, and they're investing £81 million over the next 5 years in projects that study the Greenland ice sheet and the subpolar gyre and look at tipping points and trying to build early warning systems from those. So this is a really exciting emerging area of science. But if we think back to the observations and the monitoring that Ines has showed that we can now do really effectively, then this is going to be key to building early warning systems. So we can now monitor all of those things that Ines has showed you. We can monitor the ice retreating, the ice speeding up or slowing down, the velocity of the ice. We've got those signals of thinning and mass loss, and we're now able to see hydrofracture events from the satellites more clearly. And like with the Larsen B, we see ice shelf collapse. And these, as Ines said, they show us about the health of the ice sheet, but we do need these kind of those long-term records and as detailed records as we can get of the ice sheets, because along with the sort of trends that we think we're seeing, there's also a lot of natural variability in the system, in the ocean system and the climate system, and that comes through to the ice sheets as well. So we need to be able to distinguish between a new signal or a trend emerging and distinguish that from natural variability. So we need to keep monitoring and modeling the polar regions to be able to do that. Next. And I think it's really important to note that even though we are worried about our ice sheets, they are changing, we can still avoid the worst case scenarios. All is not lost. Some ice loss is committed now. We know some more ice loss is expected, but if we can control our emissions, we can still avoid the worst case scenarios. And so I'm really happy to be able to show you here some results from the UK Earth System Model. This is from a huge collaborative effort between UK institutions and scientists and EU partners, some of which I've shown here. And this is a really state-of-the-art Earth system model. So it's the only Earth system model in the world that has a dynamically evolving ice sheet. And in this project, led by the Terra Firma team, they've used the UK Earth system model to look at stabilization and overshoot scenarios. So in the Earth system model, carbon is pumped into this system, and then it's allowed to run, and then the emissions are set to net zero once a certain temperature threshold has been reached. And that's what we're looking at with these colored lines. So the black line is the pre-industrial case, so no carbon is pumped in. And the red line at the top there, that's the case where we never get to net zero. But from the blue to the orange, we're stopping our emissions when we get to that temperature. And this is really interesting because as soon as we get to net zero, the temperature stabilizes more or less. And that also stabilizes mass loss from the Greenland ice sheet. So it's not that the Greenland ice sheet stops losing mass. In all these scenarios, it keeps losing mass, keeps losing ice over the next few hundred years. But the rate at which it loses ice is much lower if we get to net zero sooner and at a lower temperature. And that really shows us that every degree of warming matters. Every fraction of a degree of warming we can avoid keeps our ice sheets in a better state, losing mass less quickly. And we expect that also to be true for the Antarctic ice sheet. And if we start to think now, moving on from the global scale to what it means for the UK, then in this recent study, they took a storylines approach. So looking at a few sort of distinct storylines of the best different scenarios for the future. And here I've extracted some figures from this paper from 2024, looking at sea level rise at 2300 around the UK. And I want to point out straight away that the colour bar for each of these three panels is really different. So I'll walk you through that. But for this storyline A, which is a plausible best case scenario with really strong emission reductions, the sea level around the UK is sort of capped at about 1 metre by 2300. In the middle, we have a storyline C, a higher emissions scenario, but without those ice sheet instabilities. And here, it now goes up to about 4.5 metres. If we include those high-end, if we look at a high-end scenario that includes all those ice sheet instability, the marine ice cliff instability, then it's a really different picture. We're back to thinking about that 15 metres sort of level up. In fact, it's sort of 16 to 18 here, metres of sea level rise by 2300. Again, it's low likelihood, but that would be a really extreme scenario and it would affect our daily lives here in the UK greatly. And so on the next slide, we have a sort of summary plot of some of those sea level storylines and sea level rise against time here. And that dark blue line at the bottom is that best case, plausible best case scenario for reducing emissions. And the red is that high end scenario. And so the really big difference between these over an order of magnitude is really massive. And that is the risk we can still avoid if we cut our emissions and if we follow something like storyline A instead of taking the risk of increasing emissions and getting a high end scenario. And we can also zoom in even further and look what these scenarios might, or these storylines might mean for London. So this is a flood map of London for 2300. It's produced by James Savage at Fathom in collaboration with people from the Met Office and University of Bristol. And the built-up areas are shown in grey. And this is the flood risk based on a 1 in 200 storm surge event. And I should say there are no flood defences here just because we don't know what they would be that far into the future. And you can see that the blue area, which is from that best case storyline, is very different to that red area from that high end storyline. So under that high end storyline, much more of London is at risk from flooding by 2300. The flood risk goes really far out west, all the way out to Heathrow Airport. It covers a lot of central London, and it even goes quite far north up here as well. So what this is showing us is that we can avoid the future risks if we follow something like storyline A by cutting our emissions. It gives us a much better chance of protecting London and other cities around the world from the worst cases of flooding that we might see. And I just want to spend a moment thinking about the adaptation costs. So we know that the air sheets are changing, we know we need to mitigate, but we're also going to need to adapt in the future and do some adaptation. And so there was a recent report a few years ago on what will climate change cost the UK, and they used models to assess the costs of coastal impacts, rising sea level and storm surges. And they estimated that without any adaptation, by 2050, that would cost around £25 billion a year. In the case of optimal adaptation, that falls to about £3.4 billion a year. And of course, we've seen here that there's still a lot of uncertainty in how the ice sheets, and in particular Antarctica, will contribute to sea level. And so reducing those uncertainties and understanding the processes underlying them is really important. And I think it's nicely summarised by this quote from a few years ago that says there's a high economic value of reducing uncertainty through further research into the Antarctic ice shelf melting. So I just want to conclude with a summary before we take any questions. So the ice sheets are changing, they're changing now, and they dominate the uncertainties in future sea level projections. We can still avoid the worst case future scenarios for the UK if we act now to reduce our emissions. Every fraction of a degree of warming matters. It matters to our ice sheets, it matters to our daily life in the UK in the future, and it matters to our ability to adapt to rising sea levels. And this is something we can do. We can reduce our emissions and have a healthier future for our ice sheets in our country. And finally, we need to keep monitoring and modelling the ice sheets to enable timely mitigation and adaptation measures. So we want to put these measures in place to protect our people in the UK and all around the world. Thank you. I think we can now take questions, but also just briefly like to thank everyone from the working group on sea level for the NCSP that has helped put this presentation together with me and Ines.
Brilliant, thank you, Rosie and Ines. Fantastic presentation. So we're going to move to questions now. So hopefully all of you have found the kind of question tool. So it's in the bottom right of your display. There should be 9 dots, and if you click on that meeting tool, the bottom option there is a Q&A. So you can type your own questions, you can add your questions. The other thing you can do is upvote questions by giving them a thumbs up. So if there's a question that you like that someone else has posed, you can give it a thumbs up, and then we can, so I'll give it 30 seconds or so for any more questions to be asked or kind of voted on, and then we'll kind of start with the most popular first. Let's see if I can get that to refresh. Okay, so I guess what I'll do is I'll work my way down the questions in terms of popularity, and hopefully we'll get through as many as possible before we reach the hour. Okay, so first question is from Ingo Wolf, and they ask, will nuclear power plants near the coastline be safe over the coming years? Currently 3 degrees of warming is most realistic. Either of you want to offer a response to that question? Ines?
I can try. I'm not sure I can provide an answer, but I can definitely say that sea level rise is definitely of concern for all of those incredibly important facilities that are located around the coast. But what we also need to do is also to have a very good understanding of local processes around the coast of the UK as well. So we have to look, for instance, at vertical land motion, if there's any subsidence or uplift, because that would also be really important when you talk about sea level rise and when you really want to be able to pinpoint of that particular location in the UK is at risk and to estimate how much. So it will be also really dependent on sea level rise from the ice sheets, but also on those local processes. So it's still some things that's still difficult to be able to tell with certainty, but definitely some things that is of concern and that lots of people are looking into being able to advise and make recommendation on.
Great, thanks, Ines. I can add to that we do work closely with the Office for Nuclear Regulation as part of the Met Office, and we have close contacts with companies such as EDF and others. So this is something we're actively working on with them on the issue of sea level rise uncertainty. Okay, so let's go to a question from George Rees, who asks, I'm interested in how to raise understanding of climate change amongst the general public. In your personal experience, speaking with non-experts, how well does the average UK person understand the issue of sea level rise, and how helpful is the topic as a way of raising climate change awareness?
Yeah, I can give some answer to that. So I think my personal experience is very varied when you speak to people from outside our area of research. I think it varies for me, the people I meet, from people who think it's all doom and gloom, there's nothing we can do. They feel very negative. You know, they care about it, but they don't know what to do. They don't know. Some of the messaging, I think, feels like it's all too late. I think it's even just things like when you tell people the volume of ice that the ice sheets contain, I think they're always amazed. I never meet someone who's not amazed by those numbers. You know, the Antarctic ice sheet in total, we're not saying it will all melt, but has the potential to raise sea levels by 58 meters. That blows people away. They can't really imagine how much ice is stored there. So I think it's a total mix. People who think that it's all doom and gloom, people who think there's only a little bit of ice and it's not going to make much difference. I think it's a useful way of bringing up the topic of climate change. I think it is. I think that it's important to give this kind of balanced view that there is still things we can do. That even though these ice sheets are changing, even though they have a lot of potential, everything we do to slow that down and reduce the rate of loss of ice is really helpful.
Okay, did you want to offer any thoughts, Ines?
Yeah, I think I had the same experience as Rosie, because I think for most people, the ice sheets are just so far away and they're just, the polar regions, they don't really affect what's happening in the UK. But I think now more and more people realize actually the polar regions, the ice sheets are really important for sea level rise, and also like the decline of Arctic sea ice is really important because it does impact the weather that we get in the UK. So I think more and more people are getting interested in what's happening. Just because there are more extreme weather events, and we all are experiencing some changes in the climate. So I think more people are getting interested in what's happening, but then it's just being able to communicate clearly about those uncertainties, where they come from, and also what we can do about those uncertainties, because we're all working really hard, ice sheet modelers and remote sensing experts, to try to really narrow it down. Because we do want to provide more certainty about what's happening in the future, but we also make more and more discoveries about those processes. So it's just really important to communicate clearly and be able to explain where they come from. And it's really important as well, I think, to have those kind of storyline approaches or talk about risk as well, rather than uncertainty. So I think it also just depends on your audience as well and who you're talking with, and just making sure that try to communicate clearly. And I think it just really important to just insist on the fact that we can still do something if we act now to reduce emissions.
Great, thank you. I guess I could add that I think sea level rise is a challenge to communicate, because it's a summation of a number of processes, and also it tends to affect us on these longer time scales, which sometimes people feel that that's not so relevant. But I guess the key point is, we can affect outcomes many years in the future by the actions we take today on greenhouse gas emissions. So I think it is an important topic. It's obviously a very impactful topic, both in the UK but worldwide, with so many people living in coastal locations. But I think it is a challenge, but one hopefully we can help through outreach activities. So that links us on nicely to the next question, actually, from Kat Oakes, which is, so Kat is a sustainability lead at Twinkle, which is an education resource company, and they are interested from an education perspective about including recent research to educate children at all levels. And she asks, how will this information be shared with the Department for Education and to inform relevant subject specifications? So I guess we could take a general question on kind of outreach. Obviously, the slides and the kind of recording will be made publicly available, and potentially we can make these resources available. Everything we do is put in the public domain. But let's have a sort of a question on the theme of how can we use this information and latest research to feed into education and outreach? So let us know if you've got any thoughts, Ines and Rosie, on that.
Yeah, I mean, I personally think that's a really important part of all of this work, basically, is that we are communicating it to the public and to other stakeholders. But I think telling the young people, the children, about it through education is really important. And I've done quite a bit of work going into schools and giving presentations on this. And I've worked quite hard with other people here to get it in a format that is understandable for young people. And I think, again, that message that we can still do something about it is really important there. But I think there's lots of great ways we can do that now. So I was part of this big international Thwaites Glacier collaboration. And as part of that, we did some live lessons on different topics for different age ranges. And those are recorded, and then I think some of them were seen by sort of 10,000 students was the estimate. And so that they're really nice ways, because just going into select schools can only do so much, right? There's only so many of us. So having these wider outreach events that can be used in the classroom is really useful. I don't know if the NCSP has any particular plans for outreach of getting some of this stuff into education, into the younger generation, but that's definitely something I would be interested in talking about. I think it's not only to inform them, but to inspire them, and we want them to be part of the solution. We want to show them that there's things they can do, and that there's also careers in this, especially for people from different backgrounds that may not otherwise have. I mean, when I was a child, I'd never heard of glaciology or ice sheet modelling. So to bring those things to the wider community is really nice.
Yeah, thanks. No, it's a great question, and definitely on our radar to think about those aspects of education and outreach. So maybe that's something that if you wanted to get in contact, Kat, we could maybe take that conversation forward. Okay, let's go to another one. So George Rees asks about a clarification on a couple of numbers that Ines gave. So he says Ines appeared to give two different numbers: total ice sheet contribution to sea level rise of 2.8 centimeters, total mass loss of the ice sheets with 11 trillion tons, which equates to 3.2 centimeters of sea level rise. Is the difference between the 2.8 and 3.2 centimeters simply estimation uncertainty? Do you want to respond to that, Ines?
Yeah, sure. Well, thank you for paying so much attention to what I said. That's great. So the different numbers, it's actually because they refer to different time periods. So the 2.8 that I showed at the very beginning of my section was when I was looking at the global mean sea level rise record. And we do have good measurements of global mean sea level since 1993. So that number referred to the period 1993 to 2024. So that was 2.8 centimeters. And then later, when I talk only about the ice sheets, we actually can go back to the 1970s, because we have some partial coverage, but we do have some data about like ice velocity. So we still have some means of kind of estimating the mass balance before the altimetry record started. So that's why the 3.2 centimeters refers to the period 1979 to 2024. So because we added some more decades back in the past, then we have a little bit more sea level rise.
Okay, great, thank you. So Neil Kitching asks, is the UK uniquely vulnerable to sea level rise, given we are a small, densely populated island with a huge length of coastline?
I mean, I think that does make us vulnerable to sea level rise, yes. I don't think we're uniquely vulnerable. There's lots of countries around the world that are really vulnerable as well. We hear about them a lot in the news that have a really low lying or that have cities on the coast. I think, yeah, I think we are a very densely populated country. We're also lucky that we've had, if you think of the adaptation measures we have already, we've got the Thames barrier, and that's it's currently a really big success story in protecting one of our largest city from sea level rise. And I think the kind of Thames barrier estuary plans are really a sophisticated example of adaptive planning pathways. So in those ways, I think we're doing really well. But I think it's not specifically a UK problem. This is going to affect people in coastal communities all around the world.
Okay, thanks. So I'm going to move on to the last few questions I can see that come in. So someone's from an anonymous person has done a calculation and about the ice mass loss rates for the ice sheets, and they make the calculation as 22 kilotons per second. And they ask, is this useful to give a sense of urgency to the public and the state? So these, sort of thinking about these obviously quite mind-blowing mass loss rates. I guess this is probably aimed at you, Ines, primarily.
Yes, it's really important that we also try to translate our science outputs. And like, for instance, when the 11 trillion tons of ice is still a bit difficult to put into perspective. So we've tried different type of visualizations. So for instance, we say like 1 trillion tons of ice, and we try to represent it as a big ice cube, like for instance on top of London, so that people can realize the scale of the mass loss that we're seeing from the ice sheets. And we're always looking for new ways of translating basically our science that can be quite dry for a general audience into something that is more relatable, so that people can actually have a better understanding of what we're talking about and the scales of the changes that we're seeing from satellite observations. So yeah, definitely always interested in looking for new ways of visualizing this kind of things.
Okay, great. So we've got a couple of minutes left, but I think we've just got time to answer, hopefully, if we're quick on these last two questions. So both from an anonymous questioner, but the first question is, between the Antarctic and Greenland ice sheets, which is more susceptible to future changes in oceanic systems, e.g. AMOC, and how might this differential sensitivity influence their respective contributions to global sea level rise and our ability to adapt? Good question.
So yeah, I guess in terms of mass loss, so both ice sheets, they interact both with the atmosphere and with the oceans. But at least for now in the observations, we've seen that in Greenland it's more split between atmospheric processes and oceanic processes. But then in Antarctica, what really matters is what the oceans is doing rather than the atmosphere. So in the future as well, it's really important that also we've mentioned those big ice shelves in Antarctica. And it's really important that we try to better understand those ice-ocean interactions, because as Rosie mentioned, then they act as buttressing, as preventing the ice from flowing too fast into the ocean. So it will be important for both ice sheets, and particularly in Antarctica. But then what we haven't really touched upon during this webinar was also that, of course, there's also links with, for instance, when the ice sheet loses mass, it's an input of fresh water to the oceans. So what's happening in the ice sheets will also affect other components of the Earth's climate system. So it would also, for instance, affect ocean circulation by providing an input of fresh water to the oceans. And there's also a lot of research into looking at those mechanisms, because if we cross a tipping point in the ice sheet, that might also lead to crossing another tipping point in the ocean system as well. So everything is also linked in the climate system. So it's also really important that we try to understand those components separately, but also how they work together, because that will be important for the future as well.
Yeah, and I think it's fair to say that these are really active areas of current kind of research, aren't they? Kind of these investigations of how one component of the climate system can influence others, and the potential for cascading effects or the interactions between. Great question. Okay, the very last question I've got here is another anonymous questioner, but do the SSPs include feedback between ice and temperature? You talked about how ice sheet melt is factored into sea level rise projections. do land temperature projections also include the feedback to that, i.e. if we had X amount of melting which disrupted AMOC and drove temperature changes in the UK? Rosie, do you want to have a go at answering that?
Yeah, so that's a really good question as well. I think, so in some cases, yes, I guess is the answer. So when we talk about the Earth system model, I think that's where you can get into looking at effects like that. So that has the feedbacks between the atmosphere, the ocean and the ice in. And then, yes, you would be able to start to look at if the land temperatures increase and you get the ice melting, which as Ines was also just describing, it goes quite nicely with the last question, then that disrupted the AMOC, what would that do to temperatures? So it's really those big state-of-the-art Earth system models that can start to answer those questions, and the community has made lots of progress on those, but they're still very new tools that are under development and are starting to allow us to look at the big picture like that.
Okay, great. That's been a great question session. Thanks everyone who posed a question. I think we should draw it to a close there. Just a reminder that the slides and the presentation will both be circulated after this meeting, so feel free to share that with colleagues and anyone who might be interested. And thanks again to Ines and Rosie, fantastic presentation. Thanks to everyone who joined, thanks for the questions, and we'll look forward to hopefully seeing you at another webinar soon. So please sign up for the mailing list and kind of stay in touch with what we're doing here as part of the UK National Climate Science Partnership. Thank you very much.
Thank you.
Thank you.
Bye everyone.
Thank you. Bye.